steam at what temperature? 110? 20 degrees Celsius. We're adding it into how much water? 50.0 grams of liquid water. At what temp? 25. And I wanted to know how much steam I would need to add to get an equilibrium temperature, I think?
Of 9.
90 degrees Celsius?
Yeah.
It's a short version. So, thoughts? People who didn't do it preferable, let's start with that. What would we want to look at here? These types of problems, by the way, appear in a lot of the chapters because all this is conservation of energy. So we just look at energy, went from one place to another. So if I put steam at 120 and water at 25, what's losing energy, what's gaining energy? The steam will lose energy. As the steam loses energy, because it's at 120, the first thing it's going to do is cool down to 100, right? And then if there's still energy left, what will it do from there? It will condense to liquid. And if there's still room, it would cool down, right? And I know this will because I said this whole thing's going to end at 90. So the steam is going to lose energy, and it's going to do it by cooling down, condensing, and cooling down again. What's gaining energy? The liquid water. And it's only going to heat up because of where the temperature is, right? You don't have to draw this diagram, but if you do this so much stuff we keep doing. Color, any colors? I've got 50 grams of water that starts right here at 25 degrees, and I've got some amount of steam that starts at 120. The steam will cool down, condense, and cool down some more till it gets to 90, and the water will heat up till it gets to 90. How do we feel about that? So basically, just the energy lost has equal to energy gained, and we have to work the signs. So, let me try something a little different here. Let's label this as phase, step 1, step 2, step 3, and step 4, just so we can see it. And you know I'm going to do this symbolically. A fair number of these problems you can do with the numbers. And if you do it and keep track, that's fine. It's harder to keep track, especially with sig figs. And if you make a mistake, it fries everything in the next level. So it reduces your partial. I highly recommend symbolic every time. And I'm going to kind of look at it in steps first. So 1 here is the water heating up, right? So this is just a change in temperature. So 1 will be the energy in, will be the mass of the water times the specific heat of water times temperature final minus temperature initial of the water. That'll just be the energy the water absorbs. Will that be a positive or negative number? Why? Why will that be positive?
It's absorbed.
Energy is absorbed. And the math will account for that as well. The final temperature is higher than the initial, right? That's a positive number. 2 here is for the ice. Let me just kind of make a second column. 2 here is the steam condensing. That's also a temperature change. So mass of the steam, specific heat of steam, times, I'm going to put a star. Temperature final, not really, minus temperature initial of the steam. And what temperature final is that? That's actually the boiling point of water, right? That'll be 100 degrees. So I'm just going to say temperature boiling just to have it. Because temperature final really is 90, and that's not fine. As written, will that be a positive or negative number? Negative. Energy is released, and if you look at the math, this temperature will be lower than that because it cooled down, right? So that'll be a negative number. Then the condensing, I'm giving the heat of vaporization in terms of moles. I'll have the mass of the steam divided by the molar mass of water times the heat of vaporization, expressed in our units. As written, will that be a positive or negative number? As it's written.
Positive.
A positive, because all those positive numbers, right? Is energy being absorbed or released here? If something condenses, does it take energy to do that, or does it get energy out? Energy out, so that's a negative number. So I have to account for that manually, because this term just tells me the energy for phase change, not which way. And then lastly, I have to cool down the newly formed water, so it's still massive steam, which is now in a liquid phase, times the specific heat of water, times the true temperature final, minus the temperature initial, which was the temperature boiling here, and that would be negative. Do those four parts make sense? No? Which part?
I'm confused as to how you know what.
This equation.
Yeah.
What's that?
Yeah, I'm just confused as to know like what. If you're
Right
doing
now
this
for
from-
these, we really only have three equations, the one we haven't used. Q equals, and the letters can change by book, M, S, delta T. In that, M is the mass of whatever material it is, S is what?
Specific heat.
The specific heat, energy required to change one, whatever, in this case gram, 1 degree, whatever that is. The other version of this one we haven't used is Q equals N S delta T. And that's just if you did it in terms of moles. But we haven't done that in any of these.
I've seen an equation, but the S was C for specific heat.
It can be, it depends on book. Heat capacity is the amount of energy to change some amount 1 degree. Specific heat is the amount of energy to change 1 gram 1 degree, and molar heat capacity is the amount to change 1 mole. So you can change the letter, but the words really carry. Some will use S, some use C, and their substitute change. But these are the same, just those are temperature change. Phase change is Q equals, there's two versions, mass times the heat of the change, or moles times the heat of the change, depending on what H is given in. In our case, H was given in kilojoules per mole. So we're using this version. You can also, I could ask you the heat of vaporization in terms of grams or joules per gram, and you just take the 40,700, divide by 18.01528, molar mass of water, and you get the energy per gram. Is that helping? So now, energy loss equals energy gain. So I'm gonna say this equals the sum of those. And one side I have to change the sign on. Which side do I want to flip? I'd rather change this one, right? Because I don't change all those. So negative mass of the water, specific heat of water, temperature final minus temperature initial of the water, equals mass of the steam, specific heat of the steam, temperature boiling minus temperature initial of the steam, minus mass of the steam, or molar mass, times heat of vaporization, plus mass of steam, specific heat of water, temperature final minus temperature boiling. And now what am I going to solve that for? What am I looking for in this problem? Mass of the steam, and this one's fairly nice. I can factor mass of steam out of all three terms, and just divide by the difference. So without cleaning up the fraction, which I could, but I don't need to, mass of the steam equals negative mass of the water, specific heat of water, temperature final minus temperature initial of the water, divided by specific heat of steam times temperature boiling minus temperature initial of steam, minus heat of vaporization divided by molar mass, plus specific heat of steam times temperature final minus temperature boiling. And I have all those numbers. How do you feel about the algebra there? I asked that because I had 3 students in Chem 1 yesterday who had no clue how to put that as a fraction. They all got A's in every math they had. How do you feel about the algebra? Every term over here had mass of steam in it, so I just factored it out, so it left whatever wasn't there, and then I divided that onto this side. So number-wise here, you could play with the algebra if you wanted, I'm not gonna bother. So I had negative 50.0 grams water. I encourage the unit to help. Times 4.184 joules per gram degree C. 90.0 degrees Celsius minus 25.0 degrees Celsius. Divided by specific heat of steam. I told you that day, what was it? It's 2 point something. You have that handy? 2.7. I might need to put that on the formula sheet, although I don't normally use it. Do you happen to have it handy? Say it again? I'll buy that, sure. It's in that area. I can tell you what it is in calories, that didn't help any. Joules per gram degree C times 100 degrees Celsius minus 120 degrees Celsius minus 40,700 joules per mole, divided by 18.01528 grams per mole, that's the molar mass of water, plus 4.184 joules per gram UPC, times 90.0 degrees Celsius minus 100.0 degrees Celsius. Let's calculate the math.
Okay.
Yes.
Did you say how you factored out the mass of the cylinder?
Well, it appears here, there, and there. So I just factored out, so I'm left with mass of steam times that, minus that over that, plus that. And then just divided that big term here. Let's see what the numbers are. Now, I'll make one more comment, then break up and fix that. Listen. Negative 50 times 4.184 times 90 minus 25 divided by 2.07 times, I'm just related to that negative 20. Actually, I want to say times negative 20 minus 40,700 divided by 0.015 plus 4.14 times negative 10. If I type that well, I get 5.81 grams. 40,000. Accuracy. 5.81. Question for you. Let's admit numbers right, my head is okay. But why would it take so little steam to heat water up? Any idea why? Water has extremely high heat of vaporization. It takes 40,700 joules per mole, right? So steam condensing will heat up a lot of water. Which will do more damage? Don't try this at home. Which will do more damage? Take your hand and plunge it into a boiling pot of water, or hold your hand directly above it.
Hold your hand directly above it.
Why?
It's a lot more aggressive.
No, steam is at the same temperature.
One of those steam condenses under and releases heat.
Yes, but the water would do, why is it that would be more damaging?
Does it have to do with the amount of molecules that are smashing your hand?
Now, this is a big definition question. This, go ahead. That happens. Steam is less. They both, the water at the surface and steam right above it, have the same temperature. They're not even close to being the same heat. The heat above it is much higher because it's absorbed a massive amount of energy into the gas phase. Much higher heat, same temperature. Make sense? So, going from 99.9999 degrees Celsius to 100.0001 takes a huge amount of energy because you have to take all the molecules and separate them from each other. Therefore, when it condenses, from what you said, it now transfers that energy out of your hand. I shouldn't keep your hand. Does that make sense? The steam condensing in your hand releases a massive amount, goes into the cells, and the cells don't like that. So that's why it doesn't take as much steam to heat up water, because it's a lot of energy per unit of steam. If I took water at 100 degrees and did this, it would take way more. All right, last comment on this, and I told you I believe in this PGE, inappropriate social example. It doesn't stick, here's one of those. Now, ladies, this is for the guys. I'll come back to it in a second. For guys, this is sexist, it's deliberate, but we met. For guys, you know how when you're in the club or the bar and one girl comes at 9 o'clock and she's, but at 11 she comes in, at 1 a.m. she's hot. The ladies, you know the guys are always ugly, so don't worry about that. But for guys, it's different, okay? It's all time perspective, right? This is a pretty one. You may think it's ugly right now, but I promise later you'll be, God, I miss those days. This is a pretty one. Just trust me on that. All right, let's take a break. I'll see you at 1:45.
Do you have office hours after today?